On April 1st, 2025, a four-door electric sedan from a company that makes smartphones rolled onto the most feared racetrack on Earth, the Nürburgring Nordschleife in Germany, and beat a $3 million Rimac hypercar. It humiliated Porsche's flagship Taycan on its home turf by nearly 3 full seconds. It left the Tesla Model S Plaid roughly 20 seconds behind. The car was the Xiaomi SU7 Ultra. And what's about to follow is not really a story about a fast car. It's a story about how a company that didn't even build cars 5 years ago just rewrote 100 years of automotive manufacturing using an alloy designed by artificial intelligence, forged inside a 9,100-ton press in roughly the time it takes you to brew a cup of coffee. Act 1. The problem with how we build cars. To understand why this matters, you have to understand how cars have been built since the 1950s, because the answer is genuinely insane. The skeleton of every car you have ever owned is called a body in white. The name comes from the era when bodies got painted white before final assembly. And that skeleton is essentially a giant piece of folded origami. Flat sheets of steel fed into massive hydraulic presses, stamped into shape, and then welded together by an army of robots. A standard modern car body requires somewhere between 4,000 and 6,000 individual spot welds. Each one of those welds is a potential failure point. Each one is a tiny zone of thermal fatigue. Each one is an opportunity for the dimensions to drift by a fraction of a millimeter. Look at just the rear floor of the car, the structural foundation that everything else is built on. In a traditional vehicle, that single section is made of 72 separate stamped parts. Joining those 72 parts together requires roughly 840 welding points, plus meters of structural adhesive, plus self-piercing rivets, to build the back half of the floor of one car. For gasoline cars, this was good enough. For electric vehicles, it's a disaster. The moment you try to bolt a 1,000-pound lithium-ion battery into a steel skeleton designed for a lightweight gasoline engine, the physics turns against you. The weight of the battery introduces brutal twisting and flexing forces into the chassis. To fight that flex, engineers weld in heavier reinforcements. Heavier reinforcements add curb weight. Added curb weight kills range. Killed range forces engineers to install a bigger battery. The bigger battery weighs more, which requires more reinforcement, which adds more weight. Engineers have a name for this loop. They call it the weight spiral. And every legacy automaker on the planet has been trapped inside it for the last decade. Act 2. Tesla's attempt and where it broke. Tesla was the first company to look at this mess and say, what if we just stopped stamping steel? What if instead of welding 171 little parts together to form the rear underbody, we cast the whole thing in one shot, like a single piece of jewelry? They called it gigacasting. Partnering with an Italian machine builder called Idra, they built a press that could exert 9,000 tons of clamping force. Enough pressure to keep a steel mold sealed shut while molten aluminum gets violently injected into it. The results were genuinely spectacular. In going from the Model 3 to the Model Y, Tesla took 171 separate metal parts and consolidated them into 2 massive aluminum castings. They eliminated roughly 1,600 individual welds. Detroit was stunned. When Ford engineers tore down a Model Y, they reportedly couldn't believe what they were looking at. But here's where Tesla hit a wall, and the wall was made of metallurgy. The aluminum alloys used in standard die casting, things with names like A356 and ALSI-10MNMG, are brittle right out of the mold. To make them strong enough to survive a crash, the casting has to go through a process called T6 heat treatment. You bake the part in an oven somewhere between 400 and 500 degrees Celsius for hours. Then you quench it. You shock it with cold water or forced air to freeze its atomic structure. Then you age it artificially. Now that process works fine for a small engine block or a suspension arm. But when you take a single aluminum casting the size of half a car and shock it from 500 degrees down to room temperature, the part twists. It warps. It deforms. The millimeter-perfect tolerances you need to attach doors and suspension components in battery packs, they're gone. So Tesla and everyone else who copied them had to invest in massive hydraulic straightening jigs to mechanically bend the warped castings back into shape. Reports out of Tesla's Fremont factory described scrap rates so high they were causing factory fires when molten metal breached the dies. Volvo built a 6,100-ton press for the EX90. Toyota and Mercedes started prototyping their own, but all of them were trapped by the same problem. They were trying to build the cars of 2030 using aluminum chemistry from the 1980s. The press wasn't the bottleneck. The metal was. Act 3. Titan's metal and the eye that invented it. Which brings us back to Xiaomi, a company famous for making cheap smartphones. And what they did next is, no exaggeration, one of the most quietly insane stories in modern manufacturing. They didn't try to buy a bigger press, they invented a new metal. They called it Titan's metal. It's a proprietary, heat treatment-free aluminum alloy made of 11 different elements, registered in patent filings including EP4093894A1. The base is the standard aluminum silicon manganese magnesium family, but the genius is in what they added: rare earth elements, specifically cerium and lanthanum, plus traces of zirconium. This is the standard aluminum silicon manganese magnesium family, but the genius is in what they added: rare earth elements, specifically cerium and lanthanum, plus traces of zirconium. Here's why that matters at a microscopic level. In normal cast aluminum, as the molten metal cools, brittle iron-rich crystals form into sharp, needle-shaped structures inside the metal. Those needles are stress concentrators. They're the reason cast aluminum tends to shatter under impact instead of bending. The cerium and lanthanum in Titan's metal aggressively attack those grain boundaries during cooling and force the iron and silicon to crystallize as fragmented spheres instead of needles. The metal stops being brittle, it starts being ductile. The numbers are staggering. Titan's metal hits a yield strength of at least 130 megapascals straight out of the mold, elongation between 10 and over 20%, a bend angle exceeding 20 degrees at a 3mm section thickness. No oven, no quench, no straightening jig. The casting cools inside the die and comes out dimensionally perfect, and it can contain up to 30% recycled aluminum without losing performance. Now the question is, how do you discover an 11-element alloy with that exact behavior? Traditionally, this is the kind of breakthrough that takes decades. A human metallurgist mixes ingots, pours bars, breaks them in tensile machines, adjusts the recipe, repeats. For an entire career. Xiaomi did it with AI. Working with China's National Key Materials Laboratory, they built a system called the Multi-Material Performance Simulation System, internally nicknamed the Material Genome. It uses deep neural networks and a technique called Bayesian optimization to model exactly how billions of atoms behave when you melt them, mix them, and cool them. Then it ran simulations. The Material Genome AI evaluated 10,160,000 distinct alloy combinations. Try to actually picture that. If a human chemist mixed and stress-tested one alloy combination every single day, with no weekends and no vacations, it would take them more than 27,800 years to work through what the AI solved in months. The AI didn't just suggest a formula, it handed Xiaomi the chemical recipe for Titan's metal, and told them exactly how it would behave when injected as a liquid at supersonic speeds into a car-sized mold. Act 4. The 9,100-ton hypercasting machine. With the metal solved, Xiaomi needed a machine to wield it. They built one, co-developed with a Chinese heavy machinery firm called Haitian, and they named it the Hypercasting T9100. To put that in perspective, that's the equivalent of stacking over 4,000 standard passenger cars on top of a single mold and pressing down. It's roughly the gravitational weight of nearly 3 fully fueled Saturn V rockets. The machine itself weighs 1,050 tons, more than 4 blue whales, and it occupies a footprint of 840 square meters, which is roughly the area of 2 professional basketball courts laid side by side. The T9100 replaces all of it with one single component. 72 parts become 1. 840 welds become 0. The integrated floor is 17% lighter than its steel ancestor, and because there are no overlapping seams to act as acoustic resonators, cabin road noise drops by 2 decibels, meaningfully quieter on the highway. Quality control on a casting that big is paramount, because a single internal air bubble could cause the chassis to snap during a crash. Xiaomi built a fully automated inspection system around it. 9 robots equipped with Nikon laser radars and an internal X-ray system called Xi take 28 high-resolution scans of every casting in 84 seconds, with a visual AI analyzing each image in under a second. Defect detection accuracy exceeds 99.9%. Most EVs use a cell-to-pack architecture. The battery cells get grouped into modules, the modules get bolted into a metal enclosure, and the whole heavy box gets hoisted up and attached to the bottom of the car. The chassis carries the battery. The battery does no structural work. Xiaomi's SU7 uses what's called cell-to-body, or CTB, architecture. The top cover of the battery casing physically is the floor of the passenger cabin. The honeycomb of cells acts as a load-bearing skeleton. Their integration efficiency hits 77.8%, the highest CTB ratio in the world. And then they did something genuinely unorthodox. They flipped the battery cells upside down. Industry standard puts the pressure relief valves facing up toward the cabin. Xiaomi pointed them down, at the road. Why? Because in the worst-case scenario, a thermal runaway, the heat and gas and pressure now violently vent downward, away from the passengers instead of into them. The sides of the cells get wrapped in 165 pieces of aerogel insulation rated to 1000 degrees Celsius to stop fire from spreading between cells. The combined floor and battery pack ends up just 120 millimeters thick. Now bolt that load-bearing battery into a hypercast front chassis and a hypercast rear chassis, and measure how stiff the resulting car is. Engineers measure chassis stiffness in something called torsional rigidity, how much force it takes to twist a car's frame by 1 degree. The Xiaomi SU7 Ultra measures 51,000 Newton-meters per degree. To understand how absurd that is, a Ford F-150 Raptor built tough for off-road abuse sits below 20,000. The Xiaomi SU7 Ultra's number rivals a Bugatti Chiron, a $3 million carbon fiber hypercar with rigidity in the 50,000 to 60,000 range. If you bolted the rear wheels of the SU7 to bedrock and tried to twist the front axle by a single degree, you'd need the force of hanging a 5-ton African elephant off the end of a 1-meter wrench. Act 6. The 27,200 RPM motor. Now they needed something to spin all of this. Until very recently, the redline ceiling on ultra-performance EV motors, the ones in the Model S Plaid, in the Taycan Turbo GT, sat between 20,000 and 21,000 revolutions per minute. Push past that, and centrifugal force literally rips the magnets off the rotor. The 35,000 RPM motor, and whatever the material genome cooks up next, and you do not want to miss it. Until next time, keep your eyes on the road and your mind on the future.